All right, welcome to another deep dive. You guys know how this works. You send us some interesting source material, and in this case, it looks like we're going to be tackling um, some algebra,
Algebra. Yeah,
specifically factorization.
that's right.
Um,
And we've got,
I'm excited to sort of break this down. I think it's one of those concepts a lot of people, maybe learned in school,
right,
but
right.
it's always good to get a refresher.
Yeah, absolutely. And I think, sometimes when people learn these things in school, it can feel very like procedural and almost rote memorization. But there are actually some, interesting, deeper connections that are really fascinating to explore.
Yeah, yeah. I think it's easy to lose the forest for the trees when you're sort of in the thick of it, right?
Absolutely.
Like, okay, I know how to do this, but why am I doing it? And what's the big picture here?
Exactly. So hopefully we can kind of, provide that big picture context today.
Yeah, definitely. So let's, I guess, start with the source material. We've got this excerpt from a mathematics textbook, and it looks like it's really focused on like the fundamentals of factorization.
Yeah, it's really kind of like a foundational intro.
Yeah, and what's our sort of mission today? What are we trying to accomplish with this deep dive?
I think our mission is really to kind of distill like the core principles of factorization. Why is it important? What are the different methods that you can use to factorize expressions? And how does it all kind of connect to other mathematical ideas?
Okay, cool. So starting with like the basics then, I guess. The textbook starts out by talking about factors of just like regular numbers.
Uh-huh.
So, what mathematicians call natural numbers like 1, 2, 3, 4, 5, and so on.
Right, right. So like if you think about a number like 30, for example, you know that 30 can be made by multiplying different combinations of numbers. Like you could do 2 times 15 or 3 times 10.
Right, right. Or 5 times.
Exactly. And all of those numbers that divide evenly into 30, like, 1, 2, 3, 5, 6, all the way up to 30 itself, those are considered its factors.
Right,
So
right.
it's really about like what are the building blocks, the multiplicative building blocks of that number.
Right. And so then they kind of go on to talk about this idea of prime factors,
Right.
which I remember those were always like, prime numbers were always kind of interesting.
Yeah, they're kind of like the fundamental building blocks of all numbers.
Yeah. So how do they apply here?
So a prime number, if you remember, is a number that's only divisible by 1 in itself. So like 2, 3, 5, 7, 11, all of those are prime numbers because you can't break them down any further.
Right. Yeah.
And the idea with prime factorization is to take any number and express it as a product of only those prime numbers.
Got it. Got it.
So for 30, the prime factors are 2, 3, and 5.
Yeah.
Because 2 times 3 times 5 gives you 30. And the cool thing is that every number has this unique prime factorization. It's like its own fingerprint in a way.
Right. So like 70 is 2 times 5 times 7. And then 90, for example, is 2 times 3 times 3 times 5.
Yeah.
So you can kind of see how these prime numbers combine in different ways to build up all the other numbers.
Great. That's really cool.
And this idea, like this unique prime factorization, is a really, really important concept in number theory.
Gotcha. And so then the textbook makes this jump from talking about, factors of these natural numbers, these whole numbers, to talking about algebraic expressions.
Right, right. Because, the idea is that the same principles of finding factors applies to algebra as well.
Okay. So like, how does that work? Give me an example.
Sure. So let's say we have a simple algebraic term like 5 by y.
Okay.
The factors of 5 by y are 5x and y.
Because 5 times x times y gets you 5 by's.
Exactly.
Got it.
It's the same idea as before, just with variables thrown into the mix.
Okay.
And just like we have prime numbers for, the natural numbers, in algebra we talk about something called irreducible factors.
Mm-hmm. And irreducible factors are kind of like the algebraic equivalent of prime numbers. They are factors that can't be broken down any further into simpler expressions. So like, in the case of 5 by y, 5 times x times y is considered the irreducible form.
Okay.
Because you can't really simplify 5x or y any further algebraically.
Yeah.
Now, something like 5 times, parentheses xi, that's not considered irreducible because xi itself can be factored further into x times y.
Right, right. It's still like a composite factor.
Exactly, exactly. So it's all about like breaking things down to their simplest possible multiplicative building blocks.
Okay. The textbook also makes a point of talking about like the number 1 and how it's technically a factor of everything.
Right, right. Yeah, that's kind of a little nuance that's worth mentioning.
Yeah.
So technically, like 5 base y could be thought of as 5 times x times y times 1,
Okay.
but we usually don't write the 1, right? It's kind of like an implied factor.
Right, right. It's like, you wouldn't say 1 times 30, you would just say 30.
Exactly, exactly. It's kind of there in the background, but we don't need to explicitly write it out every time.
Gotcha. So we've got these, we understand now kind of the basic idea of what factors are, both with numbers and then with these algebraic expressions.
Right.
And, sometimes you'll see expressions that are already in their factored form, like, something like 3 col I, that's already factored.
Yeah, that one's pretty straightforward.
Or 5 I up y, that's just 5 times x times x times y.
Yep.
Or even something like 2x and then in parentheses y plus 2. Like that's already a factored form.
Absolutely.
On
Those are the
there.
ones that are kind of, easy to spot.
Right, but then you've got,
Yeah.
you've got the expressions like 2x plus 4.
Yeah.
Or x4 plus 5x plus 6.
Yeah.
And those are not in their
Yeah.
factored form.
Exactly.
So like how do we get
So the goal of factorization is to take those expressions that are not in factored form and find a way to write them as a product of their factors.
Yeah.
And that's really what this, excerpt is all about. What are the techniques you can use to accomplish that?
Okay, and I imagine there's probably multiple techniques
There are.
because it's not always straightforward, right?
Not always.
Okay, so what's the first kind of technique that we should be aware of?
So the first technique, and it's kind of like the most fundamental one, is what's called the method of common factors.
Okay.
And this is like your go-to first step whenever you're faced with a factorization problem. You always want to look for common factors first.
Okay, so what does that actually mean?
All right, let's look at a simple example. Let's say we want to factorize the expression 2x plus 4.
Okay.
So the first step is to kind of look at each term individually and see if we can express them as a product of their irreducible factors.
Okay.
So 2x, that's just 2 times x, right? Pretty simple.
Yeah.
And 4 can be broken down as 2 times 2.
Right.
So now we can rewrite 2x plus 4 as 2 times x plus 2 times 2. And now the key is to look for what's common between those two parts of the expression. What do you see that's the same in both of them?
I see that they both have a 2.
Exactly. The number 2 is present in both of the terms,
Right.
and that's our common factor. So just like with regular numbers, if you have two numbers that are both divisible by 2, you can factor out a 2.
Right.
So in this case, we can factor out a 2 from both of those terms.
Okay.
And what are we left with when we do that? If we take a 2 out of 2x, we're left with just x.
Yep.
And if we take a 2 out of 2 times 2, we're left with 2.
Yep.
So we get 2 times, in parentheses, x plus 2.
So 2x plus 4 is the same thing as 2 times x plus 2.
Exactly. And that's our factored form.
Okay. And that makes sense. Like if you were to distribute the 2,
Exactly.
you'd get back to 2x plus 4.
Exactly. It's the reverse of the distributive property, which you might remember from algebra class.
Right, right. So find what's shared and pull it out front.
Pull it out. Yep.
Got it. All right, let's try another one. What about 5 by psi plus 10x?
Okay, so same idea. We're going to break down each term into its irreducible factors.
Okay.
5 by psi, that's just 5 times x times y.
Yep.
And 10x is 2 times 5 times x.
Right.
Now, what do we see that's common between those two terms?
I see a 5 in both of them.
Yep, a 5 and what else?
And then an x.
And an x. So the greatest common factor in this case is 5x.
Right.
And so if we factor out a 5x from both of those terms, what are we left with?
So if we take 5x out of the 5 by, we're left with just y.
Yep, just a y. And if we take 5x out of the 10x, what's left?
A 2.
A2, exactly. So the factored form of 5 by psi plus 10x is 5x times, in parentheses, y plus 2.
Got it. Okay. So the same principle, just like figuring out what's the biggest thing you can take out of both of them.
Exactly, finding that greatest common factor.
Okay, cool.
All right, want to try one that's a little bit more involved?
Yeah, sure.
Okay, let's look at one from the textbook. They give us 12ab plus 15a.
This is where the a's and b's always start to trip me up a little bit.
Yeah, I know. It can get a little messy with the exponents, but the process is exactly the same.
Okay.
We just have to be careful with their breakdown.
Right.
So let's break down 12ABB first.
Okay.
So that's, let's see, 2 times 3 times a times b.
2 times 2 is 4, times 3 is 12, times the squared, times b.
Exactly.
Okay.
Yeah, let's do 15AB.
All right, so that's 3 times 5.
Yep.
Times a.
Times a. And then
Times b or b squared.
exactly b squared. Okay, so now we have our two terms fully broken down. Now we've got to find the factors that are common to both.
Okay.
So what do you see?
I see a 3 in both of them,
Yep, a 3.
and I see at least one a in both,
At least one a, yep.
and at least one b in both.
At least one b. So the greatest common factor in this case is 3b.
Okay.
So now we factored that 3b out of each term.
Okay.
So if we take 3b out of 12abd, what are we left with?
Okay, so we took out a 3, we took out one of the a's, and we took out the b. We're left with 2 times 2 times,
Which
which
is
is just 4a.
4a.
Okay.
And then if we take 3ab out of 15ab, what do we have left over there?
We took out the 3, we took out the a, and we took out one of the b's, so we're left with 5 and ab.
5b, perfect. So now, putting it all together, 12a plus 15ab factors into 3ab times, in parentheses, 4a plus 5b.
Okay, so you find the greatest common factor, you pull it out, and then whatever's left over goes in the parentheses.
Exactly. And it's always a good idea to double check your answer by, multiplying it back out to make sure you get the original expression.
Right, right. Okay, so let's try one more from this section. The textbook has this one. 10x EBA minus 18 egg plus 14 day. So this one's got 3 terms.
Okay, no problem. We just extend the process.
Okay.
So let's break down each term into its prime factors. So 10x XSE, that's 2 times 5 times x, right?
Yep.
And 18x AB, that breaks down as 2 times 3 times 3 times x times x times x.
Okay.
And then 14 egg is 2 times 7 times x times x times x times x.
Right.
Okay, so now looking at all 3 of those, what do we see that's common to all of them?
Okay, so I see a 2 in each of them.
A2?
And then it looks like there's at least 2 x's in each.
At least 2 x's, yep.
So I guess 2x here.
2x here. That's our greatest common factor.
Okay.
So now we factor out 2x's from each of the terms.
Okay.
And what are we left with? From 10x error, we took out the 2 and both x's, so we're left with just 5.
Yep.
From 18x psi, we took out a 2 and 2 of the x's, so we're left with minus 9x.
Okay.
And from 14x error, we took out a 2 and 2 of the x's, so we're left with plus 7x error.
All right, so the final answer is 2x of your times 5 minus 9x plus 7x there.
Exactly. You got it.
Okay, cool. I'm starting to get the hang of this.
Awesome. And, the textbook has a bunch of try these examples. So if you're listening and you want to practice this, definitely take a look at those.
Yeah, I always like those. You get to try them out yourself.
Exactly.
All right, so let's say we come across an expression where there isn't like one common factor that goes into every term.
Oh.
What do we do then?
Okay, that's a great question. So in those cases, we can often use a technique called factorization by regrouping terms. And it sounds a little fancy, but it's basically just a way of kind of cleverly rearranging the terms to find hidden common factors.
Okay, so how does that work in practice?
Okay, let's look at an example. The textbook gives us 2 by chi plus 2y plus 3x plus 3.
Okay.
Now, if you look at all 4 of those terms, there's no single factor that divides evenly into all of them, right?
Right.
So we have to get a little creative.
Okay.
So what we do is we try to group the terms in a way that allows us to find common factors within those groups.
Got it.
So we can group the first 2 terms together, 2 by xi plus 2y, and then we group the last 2 terms together, 3x plus 3.
Okay.
Now, within those groups, do you see any common factors?
Yeah, so in the first group, both of them have a 2y.
Exactly. 2y is a common factor in the first group. And in the second group, what do you see?
They both have a 3.
They both have a 3. Perfect. So we can factor those out.
Okay.
So from 2x plus 2y, if we factor out a 2y, we're left with 2y times x plus 1.
Right.
And from 3x plus 3, if we factor out a 3, we get 3 times x plus 1.
Yeah.
So now our expression looks like this. 2y times x plus 1 plus 3 times x plus 1. And now, do you see something interesting?
Oh, yeah. So now both of those terms have that x plus 1 in common.
Exactly. Now we have a common binomial factor, x plus 1, that we can factor out from the entire expression.
Okay.
And what do we get when we do that?
So we get x plus 1 times
Yep.
2 plus 3.
Exactly. And that is our factored form.
Okay, so you group them up and then you kind of factor like twice.
Exactly. You factor twice.
Go ahead.
You factor within the groups, and then you factor out the common binomial factor.
That's clever.
It's like a little puzzle.
Yeah, like a little trick.
Exactly.
All right, the textbook also mentioned something about sometimes needing to show like a 1 is a factor.
Right. Yeah, that can be important sometimes.
Like when would that be necessary?
So that comes up when, after you've done your first round of factoring, one of the groups looks like there's nothing left to factor out. So for example, let's say you had, x plus a plus bx plus b. If you factored out an a from the first 2 terms, you'd get a times x plus 1.
Right.
But then the last 2 terms are just x plus 1. So it might look like there's no common factor there.
Right.
But technically there is. You can think of it as 1 times x plus 1,
Oh, okay.
because anything multiplied by 1 is just itself, right?
Right, right.
So by showing that 1, it makes it more obvious that you have a common binomial factor of x plus 1 that you can then factor out.
Okay, so it's kind of like a visual cue to help you see what's going on.
Exactly. It makes the pattern more clear.
Got it. The textbook also says that you can sometimes regroup terms in more than one way.
Yeah, that's true.
But does that always lead to the same final factors?
It should, yes, because ultimately, multiplication is commutative, meaning a times b is the same as b times a.
Right.
So the order in which you write the factors doesn't really matter.
Right.
Let's actually try it with our previous example. So we had 2 by psi plus 2y plus 3x plus 3, and we grouped it 2 by psi plus 2y and 3x plus 3. The textbook suggests trying to group it as 2 by psi plus 3x and 2y plus 3. So let's try that.
Okay.
So in the first group, 2 by psi plus 3x, the common factor is x, right?
Right.
So we get x times 2y plus 3. And then in the second group, 2y plus 3, the common factor is just 1.
Right, because there's nothing else you can take out.
Exactly.
Okay.
So we have 1 times 2y plus 3. So now our expression is x times 2y plus 3 plus 1 times 2y plus 3.
And then the 2y plus 3 is the common factor.
Exactly. And if we factor that out, we get 2y plus 3 times x plus 1. So same factors as before, just in a different order.
Okay, that's good to know.
Yeah, so you don't have to stress too much about which way to group them. As long as you do it correctly, you'll end up with the same factors.
Got it. Okay. Here's another example from the book. 6 myc minus 4y plus 6 minus 9x. This one looks a little trickier.
Yeah, so first, always check if there's a common factor across all 4 terms. In this case, there isn't one. So let's think about grouping. The first 2 terms, 6 and phi and minus 4y, they have a common factor of 2y. So we can factor that out, and we get 2y times 3x minus 2.
Yep.
Now the last 2 terms, plus 6 and minus 9x. To try and get a common binomial factor, it might help to switch their order to minus 9x plus 6.
Okay.
What can we factor out from minus 9x plus 6 to get something that looks like 3x minus 2?
I think if we factor out a minus 3,
Yes.
then we get minus 3 times 3x minus 2.
Exactly. So now we have 2y times 3x minus 2 minus 3 times 3x minus 2, and now we see the common factor of 3x minus 2.
Right. So that's 3x minus 2 times 2y minus 3.
Exactly. That's our factored form. So regrouping can be a bit of a puzzle, but it's really useful when you don't have a single common factor at the start.
Right. Okay, so we've covered finding common factors, and we've covered regrouping. What's next?
All right, the next tool in our factorization toolkit is algebraic identities.
Okay.
And these are basically equations that are always true, no matter what values you substitute for the variables.
Right, I remember those.
And they can be really useful shortcuts for factorization.
Okay, how so?
So the textbook highlights 3 key identities that are particularly useful for factorization.
All right, what are they?
So the first one is the square of a sum, a plus b, squared equals a plus 2ab plus b.
Go ahead.
The second one is the square of a difference, a minus b, squared equals a minus 2ab plus b.
Right.
And the third one is the difference of squares, a plus b times a minus b equals a minus b.
Okay, yeah, those are all kind of familiar from algebra.
Yeah, and they're worth committing to memory because they come up all the time.
So how do we actually use them to factorize?
Okay, so the strategy is this. You look at the expression you want to factorize, and you try to see if it matches the right-hand side of any of those identities.
Okay,
And if you can find a match, then the left-hand side of the identity tells you the factored form.
got it.
So let's look at an example. Let's say we want to factorize x sub plus 8x plus 16.
Okay,
So first of all, it has 3 terms.
right.
And then you look at the first term, x up, and you see, oh, that's a perfect square.
Right, it's x times x.
Exact. And then you look at the last term, 16, and you see, oh, that's also a perfect square. It's for dinner.
Okay,
So that's already kind of hinting that it might be related to one of those identities. Now the key is the middle term, 8x.
okay.
So let's look at our first identity. A plus b squared equals a plus 2a plus b.
Okay.
If we let a bx and b be 4, then what's 2a?
2 times x times 4, so that's 8x.
It's 8x.
Oh, wow. Okay,
Right.
so it fits perfectly into that.
It fits perfectly.
Okay.
So because xx plus 8x plus 16 matches the pattern a plus 2a plus b, where a is x and b is 4,
Yeah.
we can immediately conclude that the factored form is x plus 4.
Wow, okay. So you just kind of have to recognize the pattern.
Exactly. You have to recognize the text.
And then you can jump right to the answer.
You jump right to the answer.
Okay, that's a really nice shortcut.
It is a shortcut.
Okay, so what about the second identity, the a minus b1? How would we use that?
Okay, let's look at another example. Let's say we have 4y minus 12y plus 9.
Well-
So again, three terms. And you look at the first term, 4y, Bonnie, is that a perfect square?
Yeah, because 2y times 2y is 4y wine.
Exactly. 2y squared is 4y, Bonnie.
Okay.
And then you look at the last term, 9. Is that a perfect square?
That's 3 squared.
It's 3 squared, yep.
Okay.
So again, we're kind of on the right track.
Okay.
Now, the middle term is minus 12y.
Right.
So let's look at our second identity, a minus b equals a minus 2ab plus b.
Okay.
If we let a b 2y and b go 3, what would 2ab be?
2 times 2y times 3.
Which is,
So 4y times 3, which is 12y.
it's 12y.
Oh, okay. And it's a minus 12y, so it fits the pattern.
It fits perfectly. So 4y minus 12y plus 9 matches the pattern a minus 2ab plus b, where a is 2y and b is 3. So what's the factored form?
2y minus 3.
Exactly,
Yeah.
2y minus 3.
Okay, that's pretty cool.
Right? These identities are really handy.
Yep.
Now let's look at the third identity, the difference of squares 1. That's a really useful one when you have, well, a difference of squares.
Okay.
So let's say we want to factorize 49p minus 36.
Okay, so we've got two terms,
Two terms.
and they're both perfect squares.
They are both perfect squares.
49p is 7p squared,
Yeah.
and 36 is 6 squared.
Exactly, and there's a minus sign between them.
Right.
So it fits the pattern a minus b, where a is 7p and b is 6.
Okay.
So if we just plug those values into the identity, a plus b times a minus b, what do we get?
We get 7p plus 6 times 7p minus 6.
Exactly. So 49p minus 36 factors into 7p plus 6 times 7p minus 6.
Okay, so that one's pretty straightforward once you recognize the pattern.
Yeah, once you see the pattern, it's really easy.
The textbook has this example where you actually have to use two identities.
Ooh, a double identity problem.
Yeah, so it's a minus 2ab plus b minus c.
Okay, so this one looks a little more intimidating, but it's really not that bad.
Okay.
So the trick is to look for familiar patterns within the expression.
Okay.
And if you look at the first three terms, a minus 2ab plus b, does that look familiar?
It does. That's the second identity, the a minus b one.
Exactly. So we can rewrite that part of the expression as a minus b.
Okay.
So now we have a minus b minus c.
Right.
And now what do you see?
Oh, wow. Okay. So now we have something squared
Yep,
minus something else squared.
Yeah.
That's the difference of squares 1.
you got it. So now we can apply the difference of squares identity, a plus b times a minus b equals a minus b, where in this case our a is a minus b and our b is c.
Okay.
So we get a minus b plus c times a minus b minus c. And if we simplify that, we get